Okay, thank you. Thank you for the invitation. And today I would like to share this cute story uh, uh, based on a joint work with David Gaiotto and Miroslav Rabchak. And this is section 8 in our paper. Since I only have 1 hour, so I'm not going to talk about the structure of the whole paper. Instead, I will only focus on a small portion of our work, which is fun and has some nice relation or link to some old story. As you can see in the title, the story is about Calogero model, which is known to be integrable for a long time. So, but um, I would like to first record the model. Although I believe that many of you are familiar with. So the model is described. Model describes m particles on a real line, given by the following Hamiltonian. And differential squares. This is the momentum part, the usual kinematic energy part, and there's a potential here with some parameter beta and pairwise potential like the following square, and this is known to be integrable in the following sense. Let's call it H2, i.e. it's integrable. You can find H1, which is just the total shifting operator. And H3 Hn, algebraically independent. In fact, degree as differential operator, they have, you can assign the degree hi equals to I, such that they commute with each other. You can see that this phase space has dimension 2n, and you can find this the set of n commuting operators, which is algebraically independent. Which this implies that this is an integrable model. However, well, this has been known since the introduction of this model by Calogero. However, Feynman decided to, well, in the last year of his life, Feynman was quite interested in integrable models, and he wanted to understand all this construction in integrable models from scratch by himself. So he started to look at this Calogero model, and he figured out that he could prove the integrability using his own method. Namely, he introduced the following construction. Construction of this HI. So he considered the following operator: G mu x1 xn. Del 1 plus mu plus phi x1 dot 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 del n. Let me explain the notation here. So here mu is a generic complex number. And del I is shorthand notation for del xi. And phi is a field, let's say bosonic field, bosonic free field with correlation function. Exactly given by negative beta, so to match with the convention above. So then Feynman proved the following proposition: T mu, T nu commute with each other for any mu and mu in complex number, and this will imply the following series of commuting differential operators. Namely, if you expand T mu into the following, then Ti, Tj commuting with each other for every pair of I and j. In particular, you can find that T1 is just the total shift operator. This is H1 we just mentioned. And T2, you can compute. This equals to 1/2 of T1 square minus H2. That's the Calogero Hamiltonian. And you can find highers. Ti greater than 2 has degree I. Therefore, you automatically get a family of commuting higher Hamiltonians for this Calogero model. So Feynman's way to prove this proposition is by an elementary way, just by induction and do the computation very carefully, explicitly and carefully. And he was quite unsatisfied because the proof is completely elementary and he couldn't learn anything new. And later he just summarized this in a letter to Sutherland, and it was never published till it was transcribed in 2018 by Polychronakos. And it's well, together with David Gaota and Miroslav Rabchak, we are independent working on something different. We're looking at the so-called M2 and M5 branes in twisted M theory, and we want to understand the algebra structures of local operators living on those M2 and M5 branes. We accidentally find these kind of operators and their correlation functions to popping up in our story. And then we look back into the literature to see if this has been discussed by people. And we were happy to see that Feynman has already thought about these differential operators and the correlation functions back to 1980s. And we were happy that we can provide a modern perspective on the his construction. So this is the introduction, and any questions so far? Good. Okay. Um, so so the modern counterpart of this story begins with the following. We need to introduce some kind of algebra. I'm not going to talk about the strings M series story, M series side of this story, but I'll only focus on the algebra. Namely, this is the degenerate Daha. Let me briefly recall the definition. Let's introduce Hn to be the following algebra. Let's consider a polynomial ring which has two free variables. These are just parameters of the of this algebra, epsilon, epsilon 2, and well, let us introduce this R equals to this epsilon 1, epsilon 2, so that I don't need to write it again and again. Let's form this group ring over the base ring R with respect to the permutation group, which acts on some polynomial ring. So here the action of Sn on these variables it's just by permutation, modular relations. So the relations are xi commute with xj, also yi commutes with yj, but y x on x in the following way. When I equals to j, it's epsilon 2 minus epsilon 1 times the following elements in the group ring. But when I is not equals to j, this is epsilon 1 times Sij. The reason why we introduce this algebra is because it has a nice representations. Namely, it's known that there exists injective R algebra homomorphism n fed into R Sn differential operators on n particles on C star, but they are disjoint. Namely, the xi are mapped to coordinate, the i's coordinate, and the yi is mapped to the following differential operator. So here the Sij are the permutation of i's and the j site. So this you can see that this has some similarity to the Hamiltonians. In fact, you can find you can further simplify this group ring by the following construction. Introduce E equals to the averaging of all the elements in the group ring. Then we sandwich the algebra by the action of the E on two sides. We know that E squared equals to E, so we can sandwich it E and axon sandwiched E on the right hand side. This will remove the Sn part, but gives us the Sn invariant of the differential operators. So operators on n disjoint points on C star and taking Sn invariant. And you can easily see that E summation yi E, this goes to epsilon 2 times sum of just the translation operator, and E of yi squared, this is sent to, after scaling, exactly the Calogero Hamiltonian. Here, epsilon 3 is, here notation epsilon 3 equals to minus epsilon 1 minus epsilon 2. Therefore, in our notation, beta equals to, we just move this to the other side, 3 divided by epsilon 2 squared. That's the match of parameters. So we see that we can get the Calogero Hamiltonian from this degenerate Daha. And sorry, I should introduce this part. This is called the spherical part. Spherical subalgebra. So so the crucial part of in Feynman's construction was to introduce these bosonic free fields, and we can complexify the real line, and we get a Heisenberg field on the complex plane. So namely, Heisenberg field here, living on C with OPE so here the we use some notations here. Here alpha equals to epsilon 2 divided by epsilon 1. Yes, that I'll say what it is shortly. So we introduce this notation alpha equals to epsilon 2 divided by epsilon 1. So in particular, the level equals to minus epsilon 3 divided by epsilon 1 to match with the Feynman's notation. Okay, and we introduce the following notation. Define ln mu xn, define it to be product of the following differential operator. And T and mu just the correlation function of this differential operator. So the theorem that we prove is the following. Tx0, x1, xn, this equals to E times so in particular, what the higher Hamiltonians found by Feynman is exactly the up to scaling is elementary polynomials in those yi's, and as we you can see that in the definition, those yi's commute with each other. So therefore, the commuting, the mutual commutation follows from this formula. So in fact, we can prove something slightly stronger if you can derive the following. Let me write it here. You can define the following operator, yet another series of commuting operators. Is it called Cherenkov operators? di equals to xi yi minus the following summation. You can check that they commute with each other. Then you can play with this theorem a little bit, and you can find the following corollary. You can replace the differential operator by the following I this equals to so in the each bracket you can replace the differential operators by multiply by x1 and by xi, and also multiply the fields by xy by xi. And then the effect on the right hand side is you can replace yi with those di's. And this will imply the similar construction of higher Hamiltonians of hi from 1 to n for trigonometric Calogero models. We expect that there should be a, well, it's known that version is commuting. You can replace the phi I phi j the correlation function by the Weierstrass p function, and it is known that there's a series of commuting higher Hamiltonians, but we don't know how to get it from our algebra perspective. But we do extend this result to the so-called matrix extended version. Namely, inside the degenerate Daha, you can introduce extra degree of freedom at each locations. Let me use a different color here. You can introduce GLN, or let me use GLK here, and at each location you can put the matrix there, and the grouping naturally permutes those matrices. And you can similarly define this algebra, and the Heisenberg field should be replaced by the following. You can replace Heisenberg to Kac-Moody. Let's call it J, A, B, with the following OPE. Oh, sorry, I changed it back. With the following OPE. And accordingly, you define the L and mu to be product of alpha del I plus mu plus matrix extended version of this guy, but you need to make it GLK invariant. So the way to do that is to introduce this adventure matrix EAB times JBA note that this EAB belongs to GLK, JLBI. This notation means we will assign those EAB I to the ith GLK matrix algebra. So in particular, this element belongs to a matrix extended spherical degenerate Daha. Let's call it BK. And tensor with the affine Lie algebra, GLK hot. Okay. So what I'm going to tell shortly works also in that generalized situation, namely with spin degrees of freedom. But to simplify the notation, we will focus on the case where k equals to 1, namely the Heisenberg situation. Idea of proof. Sorry? So because the cosmology split as SLN times plus the GL1 part. The GL1 part has a fixed level there, but the cosmology part has an arbitrary level. It's a generic alpha. So the idea of proof is the following. We will regard those operator L as some transfer matrix in an interval system. So namely, the classical this spin chain picture is that we have a spin chain where those Hilbert spaces V1, V2, Vn, they belongs to representation of some quantum group. Let me not specify which quantum group it is. And there's some auxiliary representation. At each point of the intersection, we can put some operators. 1, L02, 0n, and we define transfer matrix T to be well, they depend on some parameter mu, which we call the spectral parameter, T mu, to be just product of these matrices. And this will become the we just take the product and take the trace over the auxiliary space. Now this becomes element in the endomorphism of V1 tensor Vn. So this is very similar to our situation. In fact, we will show that this is exactly our situation. So Let me remove here. So here Vi are, we know that by our construction, this is the B, sorry, this will be differential operators on here in the C, and we will, well, in the tensor product, we will allow infinite sums to make sense of this tensor product, and the tensor there's a subspace which is the differential operators on m particles, but they are not allowed to collide, and as an invariant. And this is the space that the correlator that belongs to. And the auxiliary space will be the vacuum module of in the GL1 case, just Heisenberg, i.e. the Fock space. So the only remaining ingredient is what is U, the quantum group. The answer is that here the U is the Hamiltonian of GL1. In our notation, we will denote it by Y1. Okay. Questions so far? Okay. So let me briefly recall the definition. The Hamiltonian of GL1 is the R algebra with infinite set of generators, modular relations that I will not bother to write it down, but I will use an equivalent definition. It turns out that this Y1 has the same, it can be equivalently defined using the following set of generators, T and M, where N is a natural number and M is an integer. Modular relations. I'm going to write down some of the relations, but not all of them. Yes. Let's see. Yes. That will be each individual guys. So the notation 0I means the zeros vector space with the i's vector space living inside the tensor product of these two. And each individual guy lives in the tensor product of the vacuum module. Sorry, here this is the whole GL and GLK hat tensor with the differential operators living on the on one side. Yeah. It's just when k equals 1, this is the GL1. In general, it's GLK. So each L operators act on the tensor product of, so L0I acts on V0 tensor VI. So on the tensor product of the two lines that intersect here, so L0I acts on V0 tensor VI. So here the multiplication means that you contract those lines using matrix product. Yeah, in fact, it's a. So here is the trace. I would remove it. I would replace it with the correlation function on our story. So those both Vi running from 1 to n and V0 are representation of the affine union. So both the fork module and the Cherenkov algebras are the, so the Dahas are the representation of the affine union. There's a generic level we don't specify, and there's a level 0 representation. Yeah, exactly. Yes, you can do that. Yeah, this is so we specify to the vacuum space in this case. So let us mention some property of this Y1. Let's define this sub-algebra, sub-R algebra, generated by, we only take those M where M are non-negative, T0M, where both N and M are natural numbers. And then we can write down relations are the following. TPQ, RS, plus some epsilon corrections. So let me comment here is that this part vanishes for P plus Q less than or equal to 2. And in general, you can work out explicit formula exists in general. And one more factor that we prove is that Y1 is generated by A1, the subalgebra, together with T0 minus 1. And A1 is generated by T0 m greater than or equal to 0, and T2 comma 0. So you only need those lowest lying operators, T0 m, together with one extra element to generate the whole algebra. So why is this algebra relevant to our construction? This is explained by the following proposition. Part 1 is that I'll explain why those Vi for I not equal to 0 are representation of the affine Yangian. There exists R algebra homomorphism Y1 to the spherical degenerate Daha, which is uniquely determined by sending T0 m to 1 divided by epsilon 2 here n are arbitrary integers. And TPQ maps to 1 divided by epsilon 2 times 1 to n. We symmetrize those the following expression. Here PQ are natural numbers. Sorry? Okay. So here, symmetrize of XIP YIQ, sorry, XIQ YIP, meaning the following: 1 divided by the total numbers of permutations and summation of monomials in Q copies of Xi, P copies of Yi. So basically, we want something which is as averaging as possible. We want to average those because Yi does not commute with Xi. There's a choice of order, but we don't want to specify which choice of order. Then we just averaging over all the orders. And this is the part 1 of the proposition. Part 2 is that there exists R algebra homomorphism from Y1 to the Heisenberg algebra. Uniquely determined by T0n maps to minus epsilon 3 times phi n. Here phi n is the mode expansion. The nth mode in the mode expansion. And T2 comma 0 goes to the following complicated expression: epsilon square Oh, Bn is a spherical part in the trigonometric dot. This is E times E. So the punchline of these two is that proposition implies that we can regard this Ln mu and regard it as an element inside this complete tensor product. And one more ingredient we need is the coproduct. This says that there exists R-algebra homomorphism whose explicit formula I was surprised. You can look at our paper, or you can even find it in the. I should mention it earlier. This, as far as I'm concerned, this goes back to Schiffman, Lazaro, and many others of this construction of the coproduct in the GL1 case, and there exists a coproduct for higher rank as well. And therefore, Y1, you can regard this big vector space as a bimodule using the coproduct X on Bn. And so the Heisenberg, also from the right, using the opposite one. So, and the proposition that we prove is the following: L and 0 x1 to xn is an intertwiner for these two actions. Namely, it has the following intertwining property. You can act from the left using the usual coproduct. That equals to you act from the right using the opposite one. So how does this help us? there's a nice property of this coproduct. Nice fact is that coproduct of the A1 is sit inside a subspace, which is Y1 tensor with A1. And if you look at the action of this this Y1 from the left on the Heisenberg, it's let me see. Sorry, I should use this. So if you look at the formula of Y1 acts on the Heisenberg, you will notice that A1 is mapped to positive part. Namely, this part is generated by non-negative modes of the Heisenberg algebra. And this kills the vacuum. We'll see how to use this fact shortly. So proof of the theorem by playing with differential operator like this, playing with the step 1 step e to the mu x conjugated on minus mu x, we can prove for mu equals 0 only. So basically, if you conjugate it with the exponential, you can get those shifting variable mu for free. So we only need to prove the equation for mu equals 0. And step 2 is that we define the difference Gn xn to be the difference of two operators. Sorry, I put it here. So we will prove that by induction, on n show that Gn equals 0. And the n equals 1 case is obvious by the direct computation. And in fact, you can use this induction to show the following: Gn, and you just commute with one variable. And this will essentially brings you to Gn minus 1 case, which equals to 0. And this implies that this equals to 0. and the intertwining property implies that Gn commute with T2, 0. You just use this fact that Heisenberg plus kills the vacuum. So together, 4 combine 3 and 4, we get Gn commutes the image of A1. And it is known that the image of A1 contains this Euler vector field, which is sum of and this will pick out the degree of Gn, i.e. Gn commutes with is minus n times Gn. This equals 0. This implies that Gn equals to 0. So this finished the proof. And since I have already run out of time, so I just stop here. Yeah, in principle, it should be possible, but we didn't discuss it. Mm. Mm. Oh, okay. It's the spin generalization. So it's a spin generalization. So yes, yes. Let me write down here. So in that case, well, as usual, there's a kinetic term, but there's the potential is modified as following. There's some constant that I forgot. J plus nu. Let me put it. Yes, a permutation matrix. Let's say what this is. This works for this belongs to GLK times GLK. Yes, yes. There's a similar construction. Let me explain here. So so here we just use matrices and differential operators, but there's a very similar construction which essentially comes from the quantization of Nakajima equivalarities. So if you would like, this is somehow closer to the Coulomb branch side, and you can there's a Higgs branch side story, which is the following. So K is the K here, N is the number of particles, and you can form the ADHM quiver. And you can quantize this equivalarity, and it turns out that yk is the generalized version or generalization of the y1. Yk maps to the deformed quantized equivarieties. Quantization parameter epsilon 1, deformation parameter epsilon 2. And this acts on you can, for example, like this is the y, this is the x. You can localize to the place where the eigenvalue of y are distinct. Then you can get something similar to this expression. This acts on these differential operators on Cn, of course, disjoint tensor with modules of GLN, module of GLK, and take Sn invariant. And I think if epsilon 1 equals to, this will depends on epsilon 2 divided by epsilon 1. When epsilon 1 is 1, epsilon 2 equals to some level, then VL is the SL of fundamental representation. And in this case, you can write down analog of this Hamiltonian in these representations. Yes. Mm. Mm. I think this is called the vector representations. Vector representations of the affine Young of GL1. Well, you build from B1, that is the original vector representation, and you use the coproduct to build this representation on Bn. Yes. Yeah, sure. I draw a picture of spin chain, and sorry, and that's exactly the why we got exactly the place where we got the motivation. So the picture is it's about the quantum field theory in R times C2, and you can essentially forget about the C2 part, R times C, and inside R times C, effectively, the M5 brane will wrap this C plane, well, after the dimension reduction, and there will be M5 brane wrapping this R direction, and you can have multiple M2 brane, multiple these M2s, and each stack of M2 brane will support this vector representation. And for each individual M5 brane will support the representation of Heisenberg. That's the phi even here. So at the junction, this was proposed by Davide and Miroslav in their previous paper, that each junction should be this mural operator. That's exactly the operator that I wrote down earlier. So yeah, this is the picture. Okay. Thank you.